Hi everyone, my name is Moh Amer. I'm from University of Southern California. I work with Dr. Steve Cronin, and we basically work with carbon nanotubes, specifically exploring the electronic properties of pristine suspended carbon nanotube field effect transistors. So for those who do not know what a carbon nanotube is, a nanotube is basically if you have graphite and you peel off one layer of graphite, you're going to get one single layer of graphene, and if you roll this graphene into a cylindrical shape, you're going to get a carbon nanotube. Now, the way you roll this graphene can have two types, either metallic or semiconducting. And the diameter of this nanotube can range between 1 to 3 nanometer, and the length can get as high as centimeters, which you can see the ratios between the diameter and the length is crucially one of the important parameters we deal with in electrical engineering. Now, from electrical engineering perspective, what we do is we create suspended carbon nanotube field effect transistors, and the way we do this is by having a p-type silicon substrate with a pre-grown silicon oxide and silicon nitride, and then we etch a trench that is about 500 nanometer into the silicon oxide and the silicon nitride, and then we deposit electrodes on top of the silicon nitride and in the middle of the trench. So the ones on the silicon nitride are going to act as a drain of the source, and the one in the middle of the trench is going to act as a gate. And then we pattern catalyst windows on top of the drain and the source, and these catalysts actually are going to stimulate the growth of carbon nanotubes, which actually happens at 125 degrees Celsius. I want to mention the diameter of these nanotubes can actually depends on the temperature of the growth. So if you want to have a smaller diameter tubes, you can grow nanotubes at 900 degrees Celsius, and that's what we actually do. And I'm showing here the final device structure, and here's a scanning electron microscopy image of the final device structure with the nanotube highlighted in the nanotube location highlighted in the middle, and the drain and the source are the one on the corners, and the gate electrode is the shiny electrode in the middle. One of the things we observed on these nanotubes is the observation of negative differential conductance. That's basically when you measure the current by applying a drain source voltage. The current is going to decrease as you increase the drain source voltage. And we characterize how many suspended nanotubes over the trench is by this empirical formula here shown, which is 10 over L, where L is the length of the device. And if it actually follows this empirical formula, then it's an ultra clean suspended single wall carbon nanotube. We have created many devices from this device structure, nano electromechanical resonators. We also extracted the high frequency inductor. We also created a nanomem resistor, and finally we observed ballistic transport. I want to talk about the high power density of these devices. So let's calculate the high power density. If for 1 volt you get 4 microamp, and if you have a device that has a diameter of about 2 nanometer, you can find out the power per area is 63.7 kilowatt per square centimeter. Let's put this in perspective to something we actually know. And you can see here nanotubes are way up there, they're much higher than the sun's surface on the rocket nozzle. So there's enormous power being dissipated in this nanotube. And this is one of the things our devices actually compete with CMOS technology. One other aspect also is the superior electromobility and high current on-off ratio. I'm showing here for semiconducting devices the measured conductance as a function of the gate voltage. You can see the on-off ratio for this device is about 10 to the power 7. Now, if we calculate the mobility by using the CMOS equation, which is basically the differential form of the gate voltage, with respect to the gate voltage, you get electromobility that is about 7,000, which is much higher than the CMOS technology. And this is another aspect our devices actually compete with the MOSFET's devices. This brings me to the end of my talk, and thank you so much.